So let's introduce tonight's speaker. And first we have Professor Chen Li. He is a professor in computer science at UC Irvine. He obtained his PhD from Stanford University and both his bachelor's and master's from Tsinghua University. His research interests are in the fields of data management, data science, AI, machine learning, databases, data-intensive computing, and more. He was also a co-founder and CTO of a startup that was based on his research. He had multiple recipient of multiple recognitions, including an NSF Career Award and a Test of Time Award. He's also an ACM Distinguished Member and an IEEE Fellow. Accompanying him tonight is Jiadong Bai, who is a second-year PhD student of computer science at UC Irvine. His advisor is Professor Chen Li. His research focuses on building intelligent systems for big data management. His interests are integrating AI into different aspects of data science. In the Texera project, he is the lead designer of its cloud infrastructure and the storage layer, and we'll get more into that during the talk. So without further ado, Professor Chen Li and Jiadong Bai.
Okay, first of all, thank you very much for having us here. It's a great pleasure to be able to present this project to the whole audience, especially to the OC community. The big picture of this talk is about a project called Texera, which is a project our team has been building for the last 9 years, since 2016. And the main position of this system is to provide this, to support cloud-based collaborative data science and the AI/ML using workflow systems. In this talk, we allocate about 1 hour. We're going to combine some slides with a live demo. Live demos are risky because something may go wrong, the server may go wrong, the network may not work properly. But we decided to do so because we do believe having a live demo can make many things more real. And just bear with us if you encounter some technical problems. Hopefully we can solve all those issues. And also we believe the live demo is more interesting. So if we spend more time on the live demo, we might need to skip some of the slides later. So I think the live demo is more interesting. This is the outline of the talk. We're going to first use a real example to motivate the work, and we're going to talk about the live demo, and then we will discuss the backend engine called Ember, and then then after that, Jiadong is going to present the infrastructure, the cloud infrastructure we've been building to make it scalable and reliable. And then we also give a quick overview of some of the efforts we have to bring AI to the whole platform to improve the user experience. And then we're going to summarize our impact we made so far. And the live demo will be done by Jiadong and one of our team members, Chris, in the audience. So first, I'm going to use a real example to motivate our problem. Even though the example came from academic environment, the similar problems also exist in many all the other organizations, including companies. So at the UCI, we have a project, we call it mouse brain image analysis. At a high level, this is a project from the medical school. A professor, their lab is scanning the brain of a mouse, and then they produce a lot of images. And then down in the whole pipeline, later, those images have to be analyzed to build a 3D model. And using 3D model, you can do deeper analysis. So you don't need to get familiar with the details of this each step. But the idea is it's a medical project about brain image analysis. So what's the problem? The problem is about how they do this collaboration. So the name of the professor is Xiang Ming. He is from the medical school. And his expertise is in the medical domain, like mice, biology, techniques like Murfish. But they produce lots of data, and clearly lots of data are in the image modality. And analyzing this kind of data is now their expertise. For this reason, they invited another professor called Gopi. He is a professor of computer science in our department. And so these two teams, they work together. Xiaoming provides the brain image data, and Gopi his team uses their expertise in graphics, data processing to analyze data. So that's a very nice team, very nice collaboration. One issue they are facing is the language barrier. On the medical domain, they know all the technical terms about all the sequences, brain, morphage, but they have little knowledge about computer science or IT, like coding, Python, pipeline processing, parallel computing. At the same time, Gopi's team is more familiar with Python graph processing. And the way they collaborate is not very efficient. In particular, his team, they provide data, and the Gopi's team will write some code in Python, and then the Python code will be shared with the Swiss labs, some technicians. The technicians have to be very careful when they run some like a Linux command to run the Python program. So that collaboration has been not very efficient. Noticing the issue, they invited our team to come into the picture and see if we can facilitate the collaboration. So the question is, why can't we use some existing collaboration solutions available on the market? Here, I only show some of them. I think many of you are familiar with some of solutions: GitHub for source code management, Google Drive for spreadsheets, Google Docs, and Overly for people who write scientific papers, the service model. And so the question is, why can't they use this kind of already available collaboration services to do their joint work? The short answer is all these services, they're not designed for that purpose. They are not. Each of them has their own purpose, but none of them are designed for this kind of a data science, data analysis. Clearly, in the whole process, you can see the work is heavily related to data science, AI, ML, because you need to introduce some AI techniques or ML techniques to do more advanced analysis. So that's why they still couldn't find a solution to their problem. So then our team came in, and what we did was to migrate what Gopi's team has done in the Python program into this workflow. In the audience, like Yizhong and Yunyan, they're the main people who did the migration. So they successfully migrated the Python programs into this Texera workflow. This is the interface of the workflow. And then once we have this workflow available, the people from Swiss lab, they can just go to this website and use this kind of a workflow interface to do the analysis, exactly same result, but the user experience is very different. They no longer need to run some like terminal. They don't need to type in any like a Linux command to do so. I think we have some experts in Linux commands, but I hope you realize for medical people, for bioinformaticians, that's very scary to do. Right? So this is one use case of using our Texera platform to support interdisciplinary collaboration between different teams. So even though we use this example in the context of academia, you can imagine the similar problem also exists in many other scenarios. So a good example is within a company, you could have different departments, different members, and you want to work on some project. And the typical way is you do is just use like a Jupyter notebook or some R IDE environment. And now the issue there again is something very similar. These people have different experiences, different backgrounds. Some of them may not be able to write code. Some of them may be familiar with some topics like social science or criminology, but they're not good at Python or R programming. So how do we provide a platform for people with different backgrounds to work together with an experience very similar to what like Google Docs is providing? You can think about the question, can we build something similar to Google Docs, but for the purpose of data science and AI ML? So you can say that's our motivation of building this Texera project, and that we believe there are many application domain sectors that have the same problem and they can benefit from the platform we are building. So this is a screenshot of the Texera system. Later we'll see more about this system in a live demo. So at a high level, it is a GUI-based workflow. It's very intuitive. This graph has multiple boxes. We call each box an operator or step. Each operator is doing something. Different operators are doing different operations. And the developer can just put all the different operators together to construct this whole pipeline. And data will start from the source, or in general sources. It will start flowing through this pipeline until it reaches the end or multiple destinations. And each destination we call the sink. So the sink, each sink is producing some results. It could be a machine learning model, could be like a visualization chart. So then everything is happening through the browser. It's hosted by some cloud server. So from a user perspective, they don't need to download any software. They can just open the browser and then start doing this analysis and collaboration. So similar to the way we use, say, Google Docs. So that's the experience we want to enable. So next, I want to invite Jiadong to the podium, and then he's going to show a live demo with the help from Chris in the audience.
So hello everyone, I'm Jiadong. So I'm going to show you a live demo of Texera system. So Chen keep talking about collaboration between peoples. So one of the important thing about collaboration is about resource sharing. So Texera is not just an engine to do data analysis, to do AI and ML. It's also put lots of effort. We put a lot of effort on resource sharing. So that's why the Texera Hub come into the picture. So I'm going to use this website, hub.texera.io, to do this demo. We built this Texera Hub to let people publish their data analysis and also their data. With this platform, people can come to this website, check what other people have done on their research project, and be able to replicate it with just a few clicks. Now I'm going to show you. So this is the main interface of Texera Hub. We show some of the top clone workflows. Let's look at some of them. So let's pick this one. So this is a Texera workflow. This workflow is constructed by one of the high school students participating in our DS for All summer program. You can see this is how we abstract a data analysis. We're gonna know more about Texera workflow later, but you see from this interface, essentially people can publish their work. The work covers different domains like social science, like some classical machine learning examples. So suppose I'm a user, I don't have an account to Texera, so I can directly get access to these public resources. So suppose I open this workflow. This workflow is about reproducing a scientific paper about in the domain of criminology. So this workflow looks not that complex, seems to be a good starting point. Now, the way I can replicate this workflow is by having an account, which I already have, using my Google account. And then once I log into this system, I can go to this public domains. I can go to the workflow, which is about the mortality rate during the COVID time in US prison. I can click this button, and shortly the page gonna jump into this interface, which is the Texera's workspace. Let me make it smaller. Okay. So now let's check this workflow to get you more familiar with how we abstract a data analysis. So you see this graph structure here is a data science pipeline. Since it's a graph, it has a source. It also has sink. The source is the source data, where the data start to flow. And each box here is a certain operation of the data. So you can imagine the data start to flow from the source and all the way through these links to the downstream, and then finally to the sink. And at the sink, we're gonna see some results. So let me run this workflow for you. And I'm also, during the demo, I'm going to show you how people can construct a data science project, one step by step. So this is a Texera workflow after a successful execution. So you see here, are the end result we can check. So this table is from this branch. So data first is being typecasted and do some aggregation, and finally show after the sorting shows this result table. So in Texera, we model our data as tables because we think tables are probably one of the most common way of people doing this data-related project. And other than this data table, we can also see all kinds of visualization graph on Texera. Okay. So now I hope this example gave you a quick overview of what is Texera workflow, but I'm going to give you an even more detailed explanation of Texera workflow. So I'm going to create a workflow started from scratch. Now, this is a workspace I'm going to focus on in the next 10 minutes. So to do a data analysis, the first step is always to read the data. So the way people who know code may read the data by using a Python script, using some libraries, read CSV, read this file from your local laptop. That's a good way, but that's really require a huge learning step for people who don't know code. But on Texera, how you can read the data is by go to this panel. We call it a operator menu. In operator menu, you can see all kinds of operator which can be used out of box available for you. To read a CSV file, people simply drag and drop an operator here and tell this operator which file I'm going to read. So to click here, you're going to see all the datasets available on this platform. So I'm going to go to the dataset tab to show you what's available on the platform. So we have a bunch of datasets, and for this demo purpose, I'm going to use this dataset, which contain a single CSV file with a couple of columns regarding the tweets. The columns including the ID of the tweet, the month the tweet being published, how many times this tweet being retweet, being liked, and the text content of the tweet, and also the user ID, the ID of the user who published it. So let's back to our workflow. I will give it a nice name. Let's call it tweet analysis. So now back to this workflow, I'm going to read that CSV sheet we just saw. So click here, go to the demo dataset, and select the file. And now you can click Run button and see the CSV file in this workspace. Going to run it. So now the data is being loaded for you, which is exactly the same data layout we just see from the dataset tab. And also note that here is a drop-down menu here. This is the abstraction we provide for user to start their computing resources. We call it a computing unit. I already have a computing unit running which has 4 CPU and 4 gigabytes of memory. I'm going to create one for you. So this computing unit is needed when people want to execute their data science workflow. So let me just create a new one. I can select number of memories, number of CPU cores, and I'm going to click create. So while it's being created, let's keep our editing on this workflow. Now I have this CSV sheet here, which has a couple of columns. Let me run it again. Code start takes some time. So suppose I want to do a data analysis of this tweets data. Specifically, I'm interested in how many tweets are published per month. So I'm interested in how many tweets are published per month. I saw there are so many columns in the CSV sheet. There are tweet ID, there are the date the tweet is being published. Since I'm only interested in how many tweets are published at each month, I only need these 2 columns. The way I'm going to keep these 2 columns is by adding a operator called projection operator, and to only keep these 2 columns. The way I'm going to do the analysis is go to the operator panel, go search for projection operator, drag it, auto connect it, and tell this operator which columns I want to keep. So I'm going to keep the tweet ID. I'm also going to keep the month. With this operator in place, after I run this workflow, I should be able to see the data table, which is simpler than before, which contain only 2 columns. So once I run it, now the data table is much more cleaner. It has only 2 columns. I will focus on these 2 columns to do further analysis. So now I have the tweet ID and their published month. Now I need to do some counting per month on how many tweets ID are there. I'm going to add another operator to do this count for me. I'm going to add the aggregation operator here. I'm going to tell this aggregation operator what kind of operation I want to do. Specifically, I want to count how many different tweets ID are there and save it as a new column called number of tweets. And since the counting is per month, so I also need to specify the group by keys. So by configure operator like that way, after we run this workflow, we should be able to see a count of at which month, for example, February at 2022, there are 102 tweets being published. So table is good, but it's not visual enough. It's not intuitive enough. So the final step for me is to add this visualization operator. I'm going to choose the bar chart to plot this tweet posting trend. Click here. I'm going to configure it. The x axis would be the month, and the y-axis would be the number of tweets. By configuring that way, click Run button. I should be able to see this tweet trend, posting trend. Just wait. So now I have this nice visualization telling me, starting from January 2019 all the way to January 2022, what's the tweet posting trend. To make it even more colorful, I can configure it to make the color indicates the frequency. And I can run the workflow again. To see a bar chart that's even better. So now, this is how user can construct a Texera workflow. You see, during this whole process, no code is needed. From a raw CSV sheet to this bar chart, just take me 5 minutes and configuring some properties of these operators. And when we look back to this whole data science pipeline, the whole logic of this data science project is very clear. First, I load the data, do the projection to keep few columns, do aggregation on the number of tweets, and then do a visualization. So now comes to another big point, collaboration. I'm going to invite one of our team member, Chris, to join this workflow to do some editing for me. So I will click this share button. Since Chris already have an account, I will just input Chris' email. And I'm going to give Chris a read access. I'm going to share with Chris. So Chris is in the front row. Chris, please join this session. Yeah, so you see here, now the interface has some new members here. The Chris icon is showing here, and I can also see Chris cursor. This icon must look similar to you guys because nowadays we all use Google Doc or stuff. We know there's a collaborators on this canvas. So now, Chris, can you help me add a visualization of the tweets content? Maybe showing the frequency of the words.
Create a word cloud operator. And then next I'll connect the word cloud operator with the CSV file scan. Okay, and then in the property panel, I'll display the text of the tweet to visualize the text in a word cloud. Yeah,
Sure. So thank you, Chris. So now I'm going to do what Chris just helped me do by adding this word cloud operator. So I just run this branch to see the word cloud of all these tweets content. So now the workflow finished running. You can see that in this around 4.5K tweets, Johnny Mitchell seems to be the most frequent words that appear in this one. So this is how two people can do collaboration on this workflow with no single line of code. So now let me do a quick poll. How many of you guys know how to coding any languages? So it seems most of our audience know code. So I'm going to show you a feature that's more interesting. So this workflow you see during this process, I haven't written any lines of code, but since we have lots of users who are advanced coders, who want to write some complex logic, who want to train machine learning model to do inference. So we support one type of operators called user-defined function operator. I'm going to show you one of the workflow I already constructed with this UDF operators. So you see, what's the special in this workflow is there's a toolbox with the icon we are all familiar with. One is Python, another is R. Inside these operators, not just properties, we have a big section about code. So essentially, people come to this platform, if they know coding, they can customize their own operators. They can put the logic they want in this code editor. And in our engine side, we provide abstraction for people to either writing code to process those table row by row, or process the table as a whole bunch of rows. So we have those abstractions. And also, we support multiple languages because our abstraction is workflow. And inside the workflow are operator and edges. So two operators are really talking to each other using data. Data are all their common languages. So regardless of what kind of languages inside this operator is sort of neutral to other operators. So different people with different coding backgrounds can really collaborate on this workflow. If I know R, you know Python, we can really work on this same workflow together. So again, I'm going to invite Chris to show you an even better collaboration on the workflow with the UDF operators. Okay, I'm going to share with Chris. Chris, can you join the session again? Oh, I'm going to run this workflow to give you a sense of what this workflow is doing. Essentially, it's reading a classical iris dataset, and it's doing some clustering of the area of these iris species. So there's a feature on the platform called shadowing. From now on, I will basically on my screen, I will show what Chris are doing on this workflow. So Chris, maybe you can check my code to see the code content. Yes.
I'll look at the Python UDF operator and see the code content. Since this code doesn't have a comment, I will just add one line of comment what this code is doing.
Sure.
So it's computing area by multiplying length and width.
Okay.
I think the rest of the code looks good.
Sure.
Yeah.
Okay. Thank you. So you see, we are not collaborating not just on those boxes and edges. We are really collaborating on this code editor, which we are maybe more comfortable with. So that's all about Texera features. So to summarize, Texera is not just another data science tool like Jupyter Notebook. We have richer features, and we put lots of effort on data sharing workflow, which is the data analysis, share the data, and we have runtime on our system. People can not only share their data analysis, share their data, they can also invite people to join the workflow to do share editing, and we have computing resources, and people can very easily replicate what other people are doing with just a few clicks. And through this demo, you see the people construct the workflow. The way people construct it is very simple. Basically, no lines of code are needed. But if you're advanced coders, you can write arbitrary complex logics. I will show you some of the workflows some students constructed, like this one, is from the DS for All summer program. In this workflow, the student do a very complex analysis on investigating a problem, what affects high school students' GPA. You can see these students have no coding background, but after joining this summer program and learn Texera for a week, they were able to create this very complicated but very insightful workflow and produce very good results. So this website, hub.texera.io, is still in a sort of alpha testing phase, and maybe Chen gonna talk about the plan of releasing this website. And that's all for this demo. I'll hand over to Chen.
Yeah, the question was about whether we're using the actor model. I will talk briefly about it. Okay. Thank you, Jadon, for the very nice demo. So we made it. I hope the demo can give you a good idea about what this platform is capable of doing. This is just one of the deployments our team has done in the past a few months. So next, I want to use next few minutes to give you an overview of the backend, what's happening behind the scene. Okay. In particular, I will first talk about the backend engine. So if you look at the features this platform can provide, like a share editing, share execution, collaboration, there's also many other advanced features we have not shown yet. When we build a system, we look at all the available solutions on the market, in particular, those data processing engines like Spark, Flink, Kafka, and we notice none of those data processing systems can deliver what we want. So we decided to take a very kind of a brave approach by building an engine from scratch. So the engine is called Ember. And if you look at the full name of this abbreviation, actor model is a part of it. In particular, this engine has a few characteristics. First, it is an actor-based parallel processing engine. For people who are not familiar with the actor model, it's a paradigm invented back in 1970s. But recently, this computing paradigm became more mature because there are a few open source implementations that have been very successful, have been adopted by systems like Microsoft's Halo game system. People have seen, oh, this idea can be really put into practice to run in a production system to be scalable and reliable. So we took this ACT model as our bottom layer, and we built another layer on top of it. And also, it is a parallel. The reason we make it parallel is because from day one, we want to have a big vision. We want to be able to handle a big amount of data. So it's very natural for us to use a parallel engine. If you just use a single machine Python engine, then you're limited by your computing resources. One very powerful feature we didn't show is the capability of pausing one execution and resuming the execution. So what do I mean? For people who know coding like a C, C++, Java, Python, and whenever you run this kind of a complicated program, you could use print to print out all the messages and do the post-execution analysis. But very often some bugs can be very subtle. You cannot find the bugs by using the printed messages. So that's why many advanced programmers, they rely on debuggers like a GDB or a JDB, to name a few. So now, if you want to map the concept to the space of data processing, can we also enable a debugging experience for people for their data analysis? So that's why we need to have some similar features like pausing the execution of a workflow and setting some conditional breakpoint and doing some investigation of your internal state, and later you can resume the whole computation. Right? How can we bring this kind of a debugging experience in the data processing space? So this engine has that kind of capability. Of course, to show those the capability, we need a longer time to show all the advanced features. Our team, like Yishong, many other people, have done a lot of work in this space, and we can even allow people to debug the Python as one operator. We go much deeper into the execution of a Python UDF. This about debugging, we support operator level. You can pause the execution of one operator, or you can even go into one UDF operator with the Python or Python code. You can set a breakpoint at one of the Python statements. Then once the execution hits the breakpoint, the whole execution will be paused. When the user pauses the execution, we allow the user to investigate the state and modify the logic, and how to make sure the whole process is transactionally consistent. A lot of deeper issues. And we also support fault tolerance, like Sengchuan in the audience. We have done a lot of work to make this whole execution fault tolerant. And those features, if you look at what is available on the market, none of the engines can deliver this kind of experience for our users. But we believe when you do this kind of interactive data science, those capabilities are extremely important. This is a very simple example to show if I have the workflow shown on the top, very simple workflow, what the engine is converting that workflow into. The top one, you can see each box is an operator, but under the hood, that operator can become multiple workers because we do parallel computing. For instance, for this keyword search operator, even though this is a single operator, when we do the deployment, that one can become 3 threads, 3 actors, or 3 workers. So then we can use this multiple resources on a cluster of machines to get the scale up. And in one of our earlier deployments, we were able to run the whole system on a cluster of 100 machines, and each machine has 4 cores. So that deployment had about 400 cores. So the engine was able to scale to that level, right? So we are ready to handle a big amount of data. Now, this is another deeper insight of how the engine works. For this graph, where each circle is a worker or actor, within each worker, this is how internally we design the actor. There are different kinds of messages that can go into this worker. Some of them are data messages, some are like tuples from the source. Some of them could be control messages. With a control message, if the user wants to pause the execution, that request is a command, is a control message. Other control messages could be, please retrieve the state of that operator. Okay, please modify the logic of a particular property, or please resume the computation. Those requests are implemented as control messages. So inside each worker, we have different channels for different types of messages. Each channel supports FIFO and exact ones semantics. Then the whole system can do reasoning about the consistency and reproducibility. So I didn't go through detail, but back to the earlier question about the actor model. Initially, we used one actor model called Audience from Microsoft. So that's the actor model used by the Hello game system. And we did some evaluation later. We switched to another actor model called Akka, which is a Java-based actor model. And if you are interested in more details, I can talk about the details offline. So there are many other things we will not go into the details. But next, we want to pick one of the topics that could be of the interest to the audience, which is how can we scale this whole software to the cloud to be able to serve a large number of users concurrently, especially in the classroom setting when we have like 40 or 50 people, and when the platform is open to more users, we could use not just dozens of people, it could be hundreds of thousands or even millions of users. So our infrastructure and our architecture should be able to support that kind of scalability and reliability. So next, I will invite Jiadong to continue the presentation by talking about how we achieved that goal.
So now I'm going to talk about the cloud infrastructure behind the scene. So we already have a glimpse of all the nice features Texera have, including the resource sharing, the collaborative editing, and also what Chen just talked about, the interactivity on the execution level. And during the process of developing these features, we find out that these features are very attractive to lots of people, and these people are actually have very different background. These people, including the K-12 students who want to get into the field of STEM, but just don't have time to learn code. They have their high school schoolwork to do. We also find that this system is very useful to domain scientists because different technicians have different background. They have Python background, R background, but they also want to do collaboration on the same project. And finally, this platform is attractive to programmers because we have lots of computing resources. And we have GPUs, we have lots of cores and memories, and these programs want to get access to those resources and run their computing jobs. The question is, how can we scale this system? This is our initial architecture. This large box is a process running on the laptop. And these blue boxes are logical module inside this process. All those nice features are logical module inside this single process. And because it's running on some machines, it has CPU, it has GPU, it has the memories, and also the disk. This is good, everything in one place, but not scalable, and actually have lots of challenges. The first challenge is the scalability. When we provide this service to people, the service naturally have a certain access pattern. You can imagine a user come to a platform, they may want to upload their data at the first place and then start to work heavily on workflow. The traffic between the dataset module and the workflow module are quite different. The workflow module clearly have more traffic. And also different people work at different time, the traffic can vary through the time. How can we handle those traffic that are constantly changing? Clearly this architecture, because everything is in a single process, it cannot scalable independently. And plus, it's a single process. What if we want to make it a distributed? We want to add more machine. We don't have just one powerful machine. We have multiple machines. We want to deploy the whole thing on those multiple machines. How can we deal with it? So the solution is we adopt the microservice model and we leverage Kubernetes to manage a cluster of machines for us. So now each blue box, instead of being a logical module, it becomes a microservice. And since it's a microservice, which physically is a pod on Kubernetes cluster, it can be scaled up and down at any time without service shutting down. And so you see all those nice features like version control, like share editing, like workflow executions, all become microservices, become pod on this Kubernetes cluster. So with this architecture, we will successfully make this service scalable. So now, once this system becomes scalable, more and more users come to our platform, but we find out that these users actually have different computation job to run. Some users, like K-12 students, they just kick off on the STEM field. Their workflow might be very simple. But some domain scientists, they want to train machine learning model. They want to do inference. Their workflow has the Python code, which can be very heavy in terms of computation. If we host all these workflow execution in one place, there's going to be a serious computation resource competition happening. This resulting one workflow holding all the resources, but all the other workflow don't have any resources anymore. And in terms of user experience, these two users' workflow just stuck there. We don't think this workflow execution experience is good. We want to solve these challenges, which is we want to isolate the computation between workflows. The way we do it is we introduce the notion of computing unit. With this microservice computing unit manager there, every time a user wants to run a workflow, they need to send a request to create a computing unit. And this computing unit is just for that user. And that user can run multiple execution on top of the unit. So once the request goes through, this Amber runtime, which is inside a Kubernetes pod, going to be allocated for this user. So once this user wants to run a workflow, this workflow going to be sent through a bunch of proxy and arrive this computing unit, and the computation happens here. Now, another user comes to the platform, want to execute his or her workflow. This execution is not sharing this computing unit anymore. This user is running the workflow inside his or her own computing unit. With this architecture, we successfully achieve the isolation between workflow executions. And talking about lots of computation stuff, let's talk about the storage part. What kind of storage resources are involved in the execution of a workflow? So let's look at this diagram. This is a logic view of a workflow. Green shows the operator has finished running. The orange shows this operator is still running. And during this execution, there are actually two kinds of storage resources involved. For these source operators, they are usually reading a file from the file service. This file have different formats like CSV, like image, like machine learning models. But essentially, they are files. And their access pattern are read heavy, meaning user usually upload once, and multiple users are reading this set of files. And during this execution, lots of results produced. Results include the numbers, which is the metadata of this execution, and of course, some intermediate results from the operators. They are all tables. So the output of this workflow is actually tables. And the access pattern of these tables are write heavy because we have a parallel engine. These workers are concurrently writing to the same tables. So we have these two kinds of formats, files and tables. And files are really heavy, but tables are really write heavy. And our system must handle all these kinds of storage requirements. So the way we design our storage layer is by incorporating different open source resources, open source projects into this whole architecture. For files, we use S3 and LakeFS to manage those files. LakeFS manages the metadata of those files, and the S3, or more specifically, the MIO handles the actual file storage. And because of the performance of MIO, we were able to handle gigabytes or even in the future terabytes of data. And because of LakeFS, we can do version control over files. And for the output, which are tables require the write, which are very write heavy, we adopt Apache Iceberg, which is supporting the open table format and has ACID property over tables. With those components in place, we were able to handle those different storage requirements. For files, they're reading from this layer. The LakeFS manages the metadata, the MIO manages the actual file transfer. And during this execution, the output table gonna go to the Iceberg layer. So to summarize, this is the overall cloud infrastructure behind Texera. For computation layer, to support the scalability of individual microservices, we leverage Kubernetes. We also divide our service from a giant process into multiple microservices to scale them independently. To ensure the execution, isolation, and safety, we introduce the concept of computing unit, and we ensure that workflow execution from different users won't in fact other people's executions, won't have the computation of the resources. And of the storage layer, to handle those storage requirements, we adopt different open source services to handle the input files and output tables. So now that's everything about the cloud infrastructure, and Chen is going to talk about some ongoing research projects regarding incorporating AI into the system.
Thank you, Jiadong. Next, I want to mainly talk about two things. One is how to improve the user experience by using the latest AI techniques, and then I'll give an overview of the impact we have made so far. when we use the system to work with users, they give us a lot of feedback. One kind of feedback was, I still don't want to drag and drop. It's still too hard for me. So can you do something similar to what ChatGPT can do? Just one example. There are many other requests. So those requests made us think, how can we improve the user experience by leveraging the latest AI techniques? So here, I'm going to show you a few features our team is actively working on to achieve the goal. The first feature is, can we implement a chatbot interface using which people can just type in text in natural language. The system can figure out the intent and then build up that workflow incrementally. So this is work mainly led by our team member Xiaozhen in the audience. So this is about how can we have this bot for people to do something similar to ChatGPT. So what's happening behind the scene is we have another microservice on the server side, and whenever user types in something, this separate service, microservice, will talk to a large language model. It could be OpenAI, it could be our own large language model, and that large language model can interpret the input and give the output as like a JSON object, which will be converted to a workflow, or incrementally can construct a workflow operator by operator. This is a kind of a demo screenshot to illustrate what kind of experience we are targeting. As you can imagine, there are many challenges, like how to make sure the generated workflow or operators have a high quality. So we are Xiaozhen is actively working on that feature. This one looks very scary, so you don't need to look at the details. But this illustrates the current architecture Xiaozhen is using. At a high level, it's a multi-agent architecture which can divide a big task into small pieces, and each piece can be done by a separate agent. A second feature we have seen is when we work with different collaborators, a common question they ask is, I already have some Python code, I already have some R code. Can you help me move the programs into your platform? So in the past, what we have done was to look at each program and understand the meaning of the program and do the modularization and build up different operators and link them. This process can be very time-consuming. Some of the projects can take weeks, even months to finish. Clearly, that becomes a barrier. So another topic we're looking at, led by the lady who just left, Yuyan, is about how can we leverage the latest large language models to take this, say, Jupyter Notebook program and automatically or semi-automatically generate a workflow. We can significantly reduce the human effort to do this conversion. So that one is also ongoing. A third one is about when the user is in the process of constructing this workflow. At each step, can we give the user some recommendation about the next operator you could use? Even for next operator, what are the properties you can specify? This feature is, given our recent conversation with a collaborator, it is especially important when you do data cleaning. If you have a table, you can see that we have a lot of data quality issues. There are missing values, there are some non-values, or there's some inconsistent records, or you want to do the deduplication. So currently, users have to do it manually by doing the reasoning by themselves. So we want to leverage the past history of what other people have done, and by leveraging this existing large language model to be able to give some high-quality recommendations for the user in order to make the construction phase or data cleaning process much more efficient. And this is also ongoing effort. So I use these three examples to illustrate the potential of using the latest AI techniques to bring in more user-friendly experience to that platform. So at the end, I'm going to talk about the impact we have made so far and our vision. We started a project in 2016. time flies. That's 9 years ago. And the whole story was when I did a company before. I came back from my startup. I would think about what I want to do next. So this is the kind of the project I started after coming back. So this table shows some of the numbers to indicate like the impact we have made so far. Clearly, the numbers are changing. For instance, we have a huge code base with more than 100 developers, committers. Users have produced all kinds of workflows, and each workflow can have multiple executions, can have multiple versions, and we have different multiple deployments. Currently, we have more than like 6 ongoing active discussions with collaborators on different domains, like social science, biology, and brain image analysis. They all see the value of the platform in their particular domain. So we want to be the team that can provide this infrastructure for the domain. We can gain some feedback from them. Our entire research team is actually working on this project. What you see, every detail was done by somebody in the team, like even literally UI improvement, and also back to the engine side, all the very hard research problems. We have some students working on those problems. And for such a system project, we have a lot of internal conversations about the design, code reviews, quality control, in order to achieve this kind of user experience with a high reliability. Now, we look at a few sectors which could benefit from our project. One sector is education. We have used the platform to teach at least 5 courses in different contexts for different audiences. This is one called Data Science for All, or DS for All. We have offered this summer program for 2 years, and we're going to do it again this year for the 3rd time. And they are targeting high school students. So you can see this is a keystone presentation done by 2 high school students. And before they took the course, they didn't have much coding skills. And this is the final workflow they constructed. This is a course called ICS80 we offered at UCI. The instructor there is Yi Cong, who is in the audience. He's going to become a professor down the road. So in this course, we offer the content to people mainly not from CS, like math, art, biology. And in this classroom, you can see this about 40 plus students. They are using this platform concurrently to learn data science, AI, ML. From a server side, you heard what Jiadong presented. How to maintain this kind of reliability and user experience is very challenging. This is a job for us. So we view ourselves as the people at Google who build the Google Docs infrastructure. And the second sector we are focusing on is research communities. I mentioned some of them, like the collaboration between Dr. Xu and Gopi. They are in particular, we have one active project from NIH. That one is mainly for the community of diabetes researchers. And the main theme of the grant is to bring AI to that community because we all know the emerging importance of AI. And this scientific community, they also want to leverage the latest AI techniques. So we want to leverage this current Texera platform to build a platform on which they can share the data sets, share the analysis pipelines, and also share their ML models. In this way, they can easily benefit from the state-of-the-art AI technologies. So this is one of our sponsors from NIH. From day one, we have been doing the project in the open source domain. One reason was I'm a believer of using the open source path to train our students, to let them be more careful about what they build. Basically, you don't have you have nothing to hide. Everything you're doing here is in public, and you can check our GitHub repo to see the entire history of development. And we had a very high standard in the quality control, like the test cases, pull requests, reviews, and the documentation. We try our best to have a high standard. You're welcome to visit this GitHub repo to check the source code. And currently, we are in the process of donating this whole project to Apache. We are still in the process of doing the paperwork with the UCI. This will be my second project we are donating to Apache. So the last one was done about 10 years ago. It's also a kind of data processing system. So hopefully the whole process can succeed. And then if it is successful, we can initially be called this Apache portaling project. And that process may take 1 year. And after 1 year, if we meet all the standards, we could become an Apache Texera project. So this is our goal. So at this moment, I want to say this is a work of many people over many years. So I have some of my team members in the audience. If you are working on the project, you can raise your hand. This is the people some of the people who are working on the project. I want to show you, this is our official website. It's very easy to remember, just texera.io. We also have a page to show the list of the team members. So this is only a partial list. You can see over the last 9 years, many people have made a significant contribution to the code base. And we have some also new members who joined our team recently. This is our code base on GitHub. So you're welcome to check it out. With that, that will be our last slide. So I'll be very happy to take questions. Yeah, the question is how to do testing of the framework. And for people who do software engineering, we all know how important testing is. We try our best for different kinds of tests, like a unit test for each module, and do the integration test. I mean, for us, we have a kind of the backend and the front end, right? And we try to do more integration tests on the backend. But when we do the end-to-end test from the front end to the back end, that one is something we still want to improve, because it's hard to test this whole stack from the front end to the back end. And the other one is like a kind of stress test, right? So all the tests, we try our best effort. I mean, some people in the audience, like Jiadong or Yisong, if anything you want to add?
Yeah, I think for the testing, one thing we did is we have it's kind of been separate as every model. Athlete sound, but unit tests itself, fitting up. But when it becomes a service, then it's a much more harder to test, like pressure test using whatever goal that you generate is amounts. That's why we got it also. But we love to put that.
Yeah, one more question there. Yeah.
So the next question on the same line is, do you have any baseline performance test data that Texera has been tested for, say, 1 million actors and 5 gigabyte file, something like that?
Okay, the question is really about like what's the largest scale we have tried in terms of the number of actors, right? Not the size of data. These are the two different orthogonal dimensions. I want to first mention the data side because to us it's also very critical. When we build an initial prototype, most of the use cases had small amounts of data. I'm talking about megabytes or tens of megabytes, and then the process is also not very expensive. But we mainly focus on the kind of functionality. As we start talking to some collaborators, in particular, specifically in the domain of bioinformatics, suddenly we see huge numbers. We talk about gigabytes, and recently we talked about terabytes. So, and when we handle those scales, they force us to rethink about some of the design decisions. I give a very simple example. When we pass some data from one operator to the next operator, our previous solution was perfectly fine for 100 megabytes. And one use case provides 8 gigabytes, and our solution failed. And we had to think about, even now our team has been thinking about how to deliver such a large number of records and huge records on the network. And then through a network layer, Also, when you pass the information between Java and Python, and when you save it to, say, Iceberg and different layers, they all have limits. So how can we bypass the layers? And even now, our team is working on how to make the data scalable. That's a very interesting topic from both the research perspective, also from a system perspective. So the second one is really about the actors. How many actors we are doing here? So I'll first mention some of the observations. I will invite maybe Shengquan and other people to chime in. We rely on the ARCA framework. Right? ARCA, they manage the life cycle of actors. ARCA, as I said before, has been used by companies like Microsoft in some of the gaming applications. They have shown the ARCA framework can scale to millions of actors. That's one reason we decided to adopt the ARCA framework. Now, in our own deployments, we have seen numbers like hundreds. I mentioned in one deployment we had like 400 I would say workers, and each worker in our design has 2 actors. So that means in that deployment we had 800 actors, and we believe the limitation is really about the hardware. If your hardware, the cluster, as long as your cluster can handle that kind of a number, our system can benefit from that capability. Maybe Shengquan, you can chime in to mention something based on your observation.
Yes. So basically, I think for actors, they are pretty lightweight. So it's very easy to create like 100, 200 actors on a single machine, and which represents like 100, 200 workers of our operators. And yeah, that's basically what I want to say. Yeah.
Again, thank you very much. With so much information, I don't know where to start asking questions. So number one question is Texera. The name is significant because, I mean, how did you come up with the name Texera? I'm from Texas, so the moment I heard Texera,
because of
Texas,
you.
there we go. And so that's number one question. Number two, how do you guys compare to other workflow engines? There are a lot of them out there that provide that. Number three question, when I'm looking at this, you create a workflow, how does it evolve to do process observability to generate additional outcome workflows? Because, you know, process observability looks at all the data and try to create a digital twin of what the outcome is going to be. Because what I see here could potentially be applicable for a lot of stuff like Celonis does. So again, I can ask more questions, but I'm going to stop there because again,
I can answer the first 2 questions. Maybe Jiadong or maybe Xiaozhen, you can answer the third one, right? The first one is about the name, right? Name, and because you are from Texas, we came up with this name. So the real story was initially when we started the project, that's not a name. The first name was called TextDB. From name you can tell that's our original position. So when we started the project, my vision was to build a system that can combine database functionalities with text functionalities. That's our vision. And when I tried this idea, when we talk to people, we realize it's a dead end because they have different purposes. And in the middle, you also have this other solutions like Elasticsearch, and those middleware solutions, they become more reliable, more mature. Many things you could do in this hybrid can already be done by this kind of middleware solutions. Like take Elasticsearch as example, or Elastic now. And then after like a few years, we decided to do the repivoting. Based on the feedback we got from users, we realized what the people care about is, can I do something like this? And based on the feedback, we did some refinements, and this is the final. We decided not to focus on database side. This is not a database system. It's the data processing system, right? That's why it's not another Postgres, another Snowflake, another like a SQL Server. So and then we decided to rename it. We just say we try to give a meaning for it. It's called a technical error. Yeah.
thank you. I guess the reason I'm asking because you mentioned that you're going to do data cleansing as part of the process of the
Yes.
workflow. Usually in ETL, you do data cleansing before you get into the process.
Yes.
Wasn't there a reason that you guys didn't want to go with one of these databases that you can import a CSV file, have it do the data cleansing for you, because at that point your ETL or equivalent of ETL would have been much cleaner than going through the process and deduping or making sure that you don't have all the fields missing.
I mean, the different ways you can do data cleaning. You could write SQL to do everything, right? And in fact, I teach database courses. My belief, or our belief, is SQL is not designed for that purpose. But in SQL, you could use some UDFs. You can push all the logic into UDFs, like you train an ML model. You could use UDF to train the model and do the inference using UDF. But the main context is still SQL. Right? SQL is mainly for the structured query requests. Okay? The main focus is more on transactional properties, the asset properties. And SQL itself very hard for many people. And for people who know SQL, it's also very hard for them to use a SQL to specify a very complicated piece of logic, even if you use stop procedures. That's why I believe SQL, you could do it, but in many cases, like the one we showed earlier, you could use SQL, for sure you do it, but few people would do that way. That's why we decided to have a very intuitive workflow interface. And we believe that's right, one effective way to go. There are other solutions like spreadsheet, like a Trifacta. Trifacta is one example, but that's a different interface. There's a spreadsheet interface. We chose the workflow interface because of the intuitiveness and plus the cloud infrastructure. So let me get back to your second question, right? What are the available workflow systems on the market and how we are different? In the last 9 years, we have been following all the latest systems. To name a few, all the companies, each company has their own internal workflow system. But on a market, we have like a 9 RapidMiner, and also in our own city, we have our own colleagues like from Alteryx, but they all do workflow systems. There are also many workflow systems in the academia space, like Galaxy, if you're familiar with the biology analysis. We believe our system, we choose workflow as kind of more like a language, the interface to enable non-coders to do analysis. What we focus on is way beyond workflows. For example, the collaboration, right? Collaboration, the cloud. I don't require people to download any software. Everything can be done through the browser. And if you use an old solution that requires people to download the software, install the software, and then do some periodic software patches, I feel that the cloud is the way to go. This is purely my personal opinion. And then we also put a lot of emphasis on collaboration, version control, share editing, share execution. The cloud infrastructure makes those features very natural. If you have a software installation model, if 10 people have 10 different installations, many of the features are very hard to implement. But just pick a few examples to show, even though you can view us as a workflow system, our focus is way beyond the workflow as a language, and more about the capabilities behind the scene, and plus the scalability. We view ourselves as something similar to the cloud service providers like a Snowflake and Databricks, because we do allow people to elastically grab resources from the public cloud to elastically grow and shrink their computing resources to get the job done. The separation between compute storage is a very big deal for us. But before I take one more question, I will ask Jiadong and Xiaojun to answer the third question, which is how do we leverage the metadata generated from the executions?
Sure. So there's a lot of metadata when you run a workflow. You see the numbers on each operators, you see some intermediate results, and some of our ongoing research projects are leveraging those metadata to give it to AI, to let AI to give recommendations or help user construct the workflow. And that metadata we see is kind of unique, because when you write the SQL queries, SQL query essentially is being parsed into a tree during the execution time. But in the SQL interface, you don't see the result of each operator of a SQL query. But our platforms, all those metadata are very explicit, and we can choose them to send it to AI or a large language model to help user through the process.
Xiaojun, you want to add anything?
Sure. So in terms of metadata, there are 2 types of metadata in our system. One is like the whole workflow, all of the operators details, for example, like those properties you see for each operator. So in terms of AI, so we leverage these kind of metadata. Like we give AI this information to let them, like we give AI all of the available properties for each operator, and then we tell AI to generate the operator based on this information. That's one use case. If that's what Chen means by metadata. Another part is that's not like specifically AI related, but we do have a lot of statistics in our system. I don't know if that's what Chen are you referring to. So for all of the executions each user does, as you see, the whole interface is very visual. Like you see all of the number of tuples each operator processes, and then we have even more detailed information on the backend. For example, like what is the materialization size, what is the data size for each operator, and we have all of this information throughout the execution, and we log them, we store them in our databases, and we use this information to decide to like optimize to kind of do query optimization for future runs to optimize the future executions. So that's another type of metadata, if that's also considered like metadata. I don't know if this answers the questions.
Yeah.
Welcome.
Yeah, so actually my question was motivated by your early discussion. So about the comparison of workflow, I just asked, is there any benchmark or a set of metrics that I think this could make a good survey paper for you? And all the other features you mentioned could be add on, like collaboration, whatever. But is there any existing metric or benchmark that compare the workflows?
Yeah, I mean, the question is really about whether there's existing benchmark to compare different workflows. In our research, whenever we develop a new technique, we want to evaluate the solution on some workflows. So we ask exactly the same question: where can we get this kind of workflows? From our users, we have collected a lot of workflows, but still the number is limited, and we want more. There are some other online communities, they publish their workflows. We can leverage some of the published workflows to do our internal experiment. At the same time, for copyright license issues, we don't know if we can publish them because different communities have different licenses. Ideally, we keep them for ourselves. We also have some collaborations with some researchers at Oak Ridge National Lab. They have some ongoing effort of publishing some benchmarks, more like a template. Right? Each workflow can be viewed as a DAG or graph, but each workflow system can choose different implementation for that operator. So there is such an effort from Oak Ridge National Lab to come up with a whole bunch of benchmarks and let each workflow system choose their own implementation of the benchmark. So we are also part of the effort. We ourselves currently we are not putting we don't have any published workflows from our side, mainly for like privacy security reasons.
Yeah, this is how to solve the problem. Now, many times that people want to jump on the machine learning AI bandwagon, the formulation of the problem is the key. So are you working on those? So I don't know that the neuroscientist you're referring to, he probably will not get your level half the coding as not educated. But do you guide him on the formulation of the problem? What to do instead of how to do it?
I mean, it's a tough question. If you have a domain scientist like a biologist or a diabetes researcher, how can the system help them guide that process? In this case, my personal opinion is we have different expertise. Our team built a system. We have invited users. And for that kind of effort, I am a believer of collaboration. It's better to have another person who is an ML expert who can help the domain scientist develop the ML. Because if you want me to do a surgery, good luck, right? You don't let me do a surgery on you, right? So because that's not my expertise. I would rather work with somebody who knows that stuff. I can work with them. This is kind of my belief. So in that space, that's why we built this platform to enable this kind of collaboration. You do what you're good at. You let the platform combine your expertise to do something more powerful.
Yeah, I agree. It's fair to use a community that the people join for the workflow.
Correct.
Use cases that are associated to where.
Yeah, that's our vision. We do want to build a community for people to contribute their knowledge, their data, and their models. They share the knowledge, they can benefit from knowledge. And the difference from other platforms is we choose the kind of a no-coder interface. So we can invite a large population of people who don't know coding. Even for some of our members who know coding, I can tell you after they get used to this environment, this interface, they prefer this way. Because if you write Python, you can get some work done in 1 hour. If you use this platform by doing drag and drop, you can get it done in 10 minutes. Our programmers still prefer this way. It's really about the productivity. All right, so I think we run out of time. Thank you very much for your interest. Yeah.